2:01. It's 2:01, so we're pretty close to being on time. Let me say to everybody, good day. My name is Jeffrey Katz, and I'm the president of the Washington Map Society. You will hear shortly from Ron Grimm, our program chair on today's program, which is very topical, I think you'll find. And I'd like to welcome you to the program, which is hosted by a partnership of 8 map societies representing all parts of the country: the Boston, California, Chicago, New York, Rocky Mountain, Texas, and the Washington Map Societies, as well as the Library of Congress's Philip B. Phillips Society. If my screen appearance is a little odd, today it's because I'm in Seattle, Washington, actually Olympia, Washington, at my brother-in-law's house, right on the water, but the light is coming from an odd angle. Anyway, with that apology, just note that our map societies are all nonprofit organizations that support map collecting, cartography, and the study of cartographic history. And we also, all the groups, supply financial support for this Zoom meeting. So if you are not a member of any of these map societies, we hope you will consider joining at least one. And if you'll see the chat, there'll be links to the map societies' websites. The map societies vary in their benefits, and I can note that for the Washington Map Society, we are proud to have 3 annual issues of our journal, The Portal-On, which membership will provide digital access to all past issues of the Portal-On, more than 100 of them, digital access to past guest speaker lectures, and a number of other features in the members only section of our website. We have a special, an introductory rate of $25 for the first year of digital memberships, for digital membership. We also have support from advertisers, and we'd like to thank them. And they help make possible the publication of our journals, the Portal-On and the Calafia, the Journal of the California Map Society. So I hope we appreciate their support and their continued support. A couple of housekeeping measures for today's program. Please note that the lecture will be recorded. Actually, recording has started. So please turn off your video and microphone if you do not want to be recorded. Please use the chat feature to type questions, and they'll be addressed at the conclusion of both talks. And after the Q&A period, we will, as usual, leave the meeting open for a bit for people to socialize if they wish, at which point you may turn your microphone back on. And with that little introduction, I'm going to turn over the program to Ron Grimm, who is our vice president and program chair at the Washington Map Society. Over to you, Ron.
Hey, and my greetings to everybody who is attending. And it's good to see some new faces today. In consultation with several other map societies, we have developed a schedule of monthly Zoom meetings through June 2022. This schedule has not been published yet, but it will soon be included in the next issue of the Portal-On. And then I will shortly circulate it to the program chairs of the other map societies. As you can see from the slide, our next meeting is scheduled for Thursday evening, December 9th. Starting at 7 p.m. Eastern Time. It features Peter Cowdrey, who is the archivist for the Cognetta Family Trust collection of historic Florida maps in Tallahassee, Florida. The title of his presentation, which focuses on maps of Florida in the Armin Cornetta's map collection, is entitled The Florida Origins of North American Cartography. And now it is my pleasure to Introduce this afternoon's speakers. Meagan Snow, who is the geospatial data visualization librarian, and John Hessler, specialist in computational geography and geographic information science, both staff members of the Geography Map Division, Library of Congress. The title of their presentation, which focuses on mapping data from the 2020 census, is entitled Mapping Ourselves, a Cartographic Introduction to the 2020 Census and Tapestry Segmentation Analysis. John will speak first, followed by Meagan. If you have questions, you may type them in the chat feature during the lectures. John and Meagan will address a few of your questions at the conclusion of both presentations. And depending how the program progresses, we may take a few minutes break in between. Now I turn the program over to John.
Thank you. I'm going to share my screen here so we can. Everyone can probably see that. Geographic noise, database reconstruction theorems, differential privacy algorithms, and the data of the 2020 census. If you do want to put questions into the chat as I'm moving along, I will take some of them as we go along if they seem relevant to what I'm talking about at the moment. Obviously, this is going to be a two-part presentation. There's being what I'm going to be talking about here, and then of course what Meagan will be doing after. I'm going to be talking very theoretically, which is you're not going to see too many maps or visualizations in my part of the presentation here. I'm really going to be talking about what's different about the US Census in 2020 as opposed to, say, the US Census in the decades before. Over the past year or so, as many of you know, I've been doing a whole series of congressional briefings using the 2020 census data as it's being released. Some of them very specific about particular areas. I did a whole healthcare segmentation analysis for California District 13, a whole rundown of a tapestry segmentation analysis for Lorain, Ohio. We done lots of studies on internet connections and broadband mapping, where broadband across the country is, both using tapestry segmentation analysis and using the data from the 2020 census. But there's a lot different about the 2020 census data that really is what I'm going to talk to you about today, before then Meagan shows you some examples when I'm finished. And so really, when we're talking about the census and the sort of data that we're going to be using and talking about today, I don't want to sort of belabor this very much because most of you are going to know what I'm talking about here. But just to review, in case there are people who are attending who don't really understand what this data is and how it works, obviously there's the decennial census, which is every 10 years. Everyone knows about that, used for redistricting and all kinds of other things. But then there's something the census also runs called the ACS, or the American Community Survey, which is a lot more detailed. There's about 300 surveys that go out every month. They're released in 1, 3, and 5 year estimates, and they're much better at allowing us to see how things change over time. And that is really the central portion of really the way we use the census data. We use it in combination with the ACS in order to be able to understand things and map things like, as I said, broadband access, and a whole bunch of other kinds of demographic data. We've done presentations on healthcare, on child poverty. I just did one, as I said, on Lorain, Ohio, which is purely on deindustrialization and how that has changed over the last couple of decades. So this is the kind of thing that over the last year we've spent a great deal of time doing. There's a new program which has been instituted by the Congressional Research Service and the Congressional Relations Office at the library. And about twice a month now, I'm giving programs basically trying to get them to understand how to use not only census data, but the ACS data and other authoritative data sets to sort of visualize what's going on in their districts, get a better idea of what their districts look like, and get a really deep dive into the sort of geography of their districts. This has been really well received, as a lot of you know. But this year, the census.
It stopped. The pictures are
All right,
still.
for some reason I got muted there. I don't exactly sure what happened, but we seem to be having an in and out with our internet service at the moment. But anyway, the 2020 census is very different, and it comes down to a couple of reasons for that. Obviously, it's the most advanced census that the U.S. Census Bureau has put together. There's lots of things that have gone into it: machine learning, agent-based modeling, all kinds of very detailed things, which have allowed the census data to really bring itself into the sort of modern era of big data. And this has created several problems, and we're going to talk about those. I'm going to talk about those in just a minute. But the central issue that is the problem is really something called database reconstruction theorems. And I'm going to talk in detail about what that means, because it's critically important to how people like myself and other people who are using the census data for analysis and for legislative work and any work in general that the census data comes into policy, the policy realm, this becomes extremely and critically important. Mostly because the US Census has begun to inject noise into the data. And this is something, like I said, that's going to be the whole point of what I'm going to be talking about to you now, is this idea of injecting noise into the census data and why that is done. There are invariants. In other words, there are things that the census data has said are not going to be changed. In other words, they're not going to put noise into them. And this will become apparent when I'm talking about in just a bit, what an invariant is and why that's important. And the reason the census data is being made noisy, and like I said, I'll define that in just a bit, is really because of this discovery a few years back of something called database reconstruction theorems. And I'll talk about that in just a minute. But also remember, there are these invariants. There are things that the census data isn't changing, and they're not changing those things simply because for policy decisions that have been either legally dictated, or things like redistricting, where noise into the data would be very difficult to deal with for the people who are doing redistricting and other things that have been legally mandated. And so we're really going to be talking about a conflict here, at least in my part of the presentation, between two types of data. One called small area data, which is sort of the census tract data and the block data, and something called microdata. And microdata is the attachment of the statistical data to an individual. So if one thinks about what the census actually is, the census releases a series of tables. All those tables are statistical. All those tables present, here's a percentage of people under this age, here's how much they make. And it doesn't attach anything to a single human being. But in fact, all of that data is attached to a single human being. But the census doesn't want anyone to discover who those single human beings are. In other words, who the identity of the people who've given the microdata are. And this has not really been an issue until recently, obviously, with extremely good brute force algorithms and statistical learning algorithms. There are people who've been able to actually reconstruct individuals' names attached to census data from the statistical table. So this is not stealing data. This is not somehow getting data that other people don't have. It's just you take a whole bunch of the census statistical tables, you put them together, and you're able to reconstruct individuals' identities. And I'm going to show you how that works and why that has been so important and why that's so controversial in the census right now. This is something that the American Association of Geographers has taken some stands on. In the annual meeting next year, there's going to be multiple programs which are going to be discussing these algorithms, discussing the what effect these kind of algorithms are having on the data themselves. There's lots of people. Next week actually is GIS Day. It's this, Geography Awareness Week is next week. And of course, GIS Day is right in the center of that on Wednesday. The Library of Congress is going to present 4 papers, which are going to be dealing very much with the census data, the modern census data, and the effect of these reconstruction algorithms. The keynote speaker will be the chief of the geography division of the census, who will be talking about some of the agent-based modeling that has been done in order to see what the actual effect of the noise that's been injected is. So these database reconstruction algorithms really, or theorems, really what they are is in 2002, 2 statisticians, Demure and Meason, came up with these mathematical theorems, and they frankly proved that if one has enough statistical data, there is always a mathematical solution. In other words, always a unique solution. If I take all these data tables and I put them together, I can find a unique solution that will identify each of the individuals. In other words, I will be able to reconstruct the micro data that the census had that actually went into the statistical tables themselves. It was a groundbreaking and important paper, and it really made the census worried. During the 2010 census, there was some attempts to take care of this, attempts to think through this and how this might affect it. But it really is only been recently that the census has been able to actually come up with a way to actually combat this. So when we think about this, and I'm going to not go into too much detail here, but there's this sort of continuum between privacy and accuracy. So if I want no accuracy, I can have 100% privacy. If I want 100% accuracy, I will have no privacy. And the key is to somehow, by the way, if you're hearing that in the background, we're having a huge thunderstorm here right now. So hopefully nothing will go out. So there's this balance between privacy and accuracy. And the key for the census was to come up with a way to figure out how to inject enough noise. In other words, to perturb the accuracy of the data so privacy would be preserved, but yet at the same time that there would be enough accuracy to make the census data useful. Now, of course, the best way to preserve 100% privacy is to release no data. But that is not a reasonable thing for the census to do. It sort of defeats the entire population. But these database reconstruction theorems basically said that mathematically, there is no reasonable definition of privacy that can be maintained if you want complete accuracy in the data. And this is a groundbreaking, revolutionary group of mathematical theorems that really put people on edge about the census data. These reconstruction attacks, which have happened continuously using the 2010 data and using some of the other data that's been released through the years, when they are combined with third-party data, so things like voting records and things like that, it becomes completely possible to basically reconstruct for a single person how much their house costs, how long they've lived there, almost any possible piece of data you want based on a household, so based on an address. And so that's what the census data was really attempting to stop. So if we look at a typical census data, and I'm just going to use this very simple example to show how this plays out. So if we look at something like this is just a count of 7 people. So let's say this is just a block. In other words, this is 7 households, seven things in just a block in a city or somewhere. So we have these, whether they're male or female, whether they're Black or African American, white, single, married, the typical type of census data, whether they're under 5 years of age, whether they're under 18 years of age, you know, the typical kind of statistical information that you see in a census table. Now, this is all statistical data. There's no individual records here. I can't construct an individual. I can't tell which member of the population who's female, one of those 4 females is also white or single because it's statistical data. Okay, but all the records here are derived from one-to-one mappings. In other words, they're mappings from a single person into the statistical table. And the question is, can I take this table? And even though that I've taken out the substantial amount of information that you see, so I have suppressed all of the information in the bottom of the table. So I've suppressed what the single adults are. I've suppressed the Black or African American male, whether you're a white male, white female. I've suppressed all this data. And the question is, can I take this table and just using this table, can I reconstruct the individuals? In other words, what each individual in this set is. And if I can, is it a unique reconstruction? In other words, so when I do this reconstruction, do I get one solution that gives me the identities of all 7 people in this set? And according to the database reconstruction theorems, I should be able to do that. I can, okay? So the database reconstruction theorem is what we're going to just talk a little bit about here. And I'm just going to, like I said, show you this as an example, and then just show you the kind of effect the algorithms that are being used actually have on the census data. So the database can be reconstructed by treating these things as attributes of person, living on a block as basically this collection of variables. And I then make a set of constraints, which is extracted from the table. And these constraints basically are the various things that are in there. What is the median? What is the mean? If I've got in the table, as you see here, there's both a median and a mean, which means I can construct actually sets of numbers associated with that. What are the range of possible ages that have a median of 30 and a mean of 38? What percentage of females have a median age of 30 and a 35? So I can actually reconstruct all of these attributes. Okay, now if these attributes are constrained, which what we're talking about are constrained attributes, they have ranges, they don't go all over the place because the census releases these medians and means. I can basically say, well, to have a median age of 30 and a mean of 38, there has to be a certain range of numbers, so it's constrained. And so basically to mount a full reconstruction attack, I basically extract all these constraints, and then I make a single mathematical model that allows me to reproduce all of the microdata. Now, when we're talking about the census, of course, these are billions of pieces of data. But today, the amount of data that's in the census is not that large compared to the amount of data that can be really manipulated. And really, when we're talking about the data that is on the block level or the census tract level, so a census tract is typically between 1,200 and 8,000 people. The census likes to keep it at around 4,000, which is why in the cities, they're very small, and in the rural areas, they're very big aerially. But can we take some of those and reconstruct every individual's identity and all the attributes that each individual person has out of this? And yes, in fact, there is a unique mapping into the original data. Now, the way this is done is there's something called the satisfiability solver that an attacker is going to use. So I basically transformed this problem into a single Boolean formula. And in the case of the thing that we're working on right now, this 7-person, basically reconstructing that thing, I have 6,755 variables, which are arranged in 252,575 Boolean clauses. In other words, these are if-or statements, okay? And basically then the database reconstruction theorem says there exists a solution universe, okay, of all possible solutions of this set of constraints. So what I'm looking for is not the universe of possible solutions, because there's lots of possible solutions that might satisfy these 6,755 variables that these 7 people have. But there may be a unique solution. So my job as the person who's attacking this database is to come up with the unique solution. If I have 4 or 5 solutions, that's not going to help me because I'm just not going to be able to know which one is right, and it doesn't really help me. So what the census is trying to do, it's trying to prevent me from reconstructing, or an attacker, not me personally, an attacker from finding that unique solution. So it's going to inject noise into data to throw people off the track. So if we just look at this quite simply, the database reconstruction theorem says there is a solution. So if I put no noise into this whatsoever, okay, if I don't do anything whatsoever to the data, and I just use my original table, even with all of this information removed. Using a satisfiability solver, which is a real brute force way of doing this, I can basically find a unique solution out of the hundreds of thousands of possible solutions. So no noise has been injected into this table. So this is the table as the census would have released it, suppressing data. So the first idea that the census had was, in fact, okay, what we're going to do is we know these are possible. We're going to suppress some of the data. So we suppress some of the data in the table. People won't have access to this data in this particular table. They may have access to it in another table, but we'll mix this data up. But what happens is, even with all of this data suppressed, using a satisfiability solver that I just described, and just simply solving these 252,575 clauses, and I'll tell you, working in with the Mathematica-based or the MATLAB-based satisfiability solver, it took on just a regular computer using just a couple of GPUs, so not super high performance computing. It took about half a second to solve this. And here's the unique solution. So this is the identities of each of these people. So the first person is age 8, sex female, race black, marital status single. So this is all of the attributes of each of the individuals. So what I've done is I've taken this statistical data, turned it into this huge Boolean expression, solved the massive set of equations, and this is the solution that I get. Now, all I would need to do, because I know where this is, so I know the addresses of each of these things. This is a block. This is, a set of 6 or 5 or 7 houses. All I need to do now is to match this with something like voting records that are publicly available or real estate records, and I have the names and I have every attribute of this particular person. Now, we're working with a small database here. We're only working with these 4 variables, but this can be extended and generalized to the hundreds of variables the census collects. And what I would have is I would have for every single person in the United States, if I did this well enough, I would have all of the census data back down to the original person who sent it. Now, obviously, there's a lot that can be done with this data, but of course, what scares the census's data is if this is possible, people are going to be less honest on the census forms, because if I can reconstruct every answer to all of the questions that you gave using these methods, which according to the database reconstruction theorems, I can find a unique solution, this is a serious problem. So what does this mean? How do we stop this from happening? And so what basically the census started doing is, okay, let's drop a few more things. So let's take all of these things again that I dropped from the statistics, and now I'm going to drop these 2 statistics. So I'm going to drop whether you're male or female. If I drop those 2 out, okay, I then reconstruct the database records for 4 of the people. So I can still infer 4 of the 7, even if I drop the statistic on male and female. So I've dropped all of this data. I have now dropped whether they're male and female, but I can still reconstruct perfectly 4 of the people's identities, which is not good enough for the census. It's not good enough as something that, of course, the census says they are maintaining the privacy of the individual microdata records. They're giving you small area statistics, but they're maintaining privacy on these individual records. So this is a huge issue. So I could still infer 4 of these. Now, what the census does then begins to do, it says, okay, I'm going to remove another one of these statistics, okay? And when I remove another one of those statistics, the decision process gives 2 solutions. So when I remove 4A, so now I've gotten rid of a whole bunch of stuff, and it's only getting rid of that material, getting rid of that much stuff, that has allowed me now to not have a unique solution, which means now we have privacy, because I now have 2 solutions where none of the solutions are the same. Each of these solutions represents the statistic in the table, but it will not allow me to identify the individuals. Of course, this is a very simple model, like I said before, and the simple model is something that obviously when we're talking about simple models, It's very different than when I'm talking about the whole census, because there would be literally hundreds of these solutions, thereby not making it worth anyone's time to try and reconstruct this data. And so that's what the census is trying to do. Now, the way they're doing it is a little bit different than introducing, in other words, taking things out, but it's somewhat the same. And what they've been using is something called the top-down algorithm. And I'm not going to go into what top-down does, but what it actually does is it injects noise. So there's three possible ways that we can fight a database reconstruction attack on census data. One is to publish less data. One is to input noise, and one is to have input noise injection, and one have output noise injection. So in other words, when the census produces the tables, it can put noise into the tables to make them unreconstructible, or it can, when you take the output, it can inject noise in order to have the output data being noisy. Either way, these are the three possible ways. Now, publish less data, the census did not really think is an option, because this data is, of course, critically important to almost everything that happens in the United States. Everything from healthcare to how transportation funds and everything else is allocated in our system of government has to do with the census. It has a huge impact on things like redistricting and things like that. There were a lot of scholars who were very worried about what effect this sort of injection might have on the actual redistricting that will take place. There have been a bunch of studies right now, most notably by Moon Duchin at Tufts, showing that there's very little effect of the top-down algorithms on the actual redistricting process, which is extremely important to know. One of the invariants is actually the gross population in each of the census tracts, which is very helpful. And also the amount of buildings and occupants. So that is invariant. There's no noise injected, but all the other census data now has things that are that have noise injected into it to prevent these kinds of attacks. The top-down algorithm has been very difficult to study analytically. There's a couple of us working on this problem right now. The GIS day that's going to take place next week, I talk about some of the problems in trying to study the algorithm analytically, in other words, from a purely mathematical standpoint. Duchin and her team were really using the data empirically and proved that the algorithm didn't affect it too much. But it's been very hard to study analytically. And of course, lots of mathematicians, computer science, and geographers have really turned their attention to this right now. And as I said earlier, the AAG next year is going to have lots of sessions on just this problem itself. So there's a lot of things that it does affect. There's been a lot of papers put out on how it affects sort of health disparities. Some of the things that I've been talking about to congressional staff, especially when talking about COVID-19 and mortality rates. Differential privacy in the census has distorted some of the mortality rates in very strange ways, but at least we can track them and we can show and figure out how they work. An example, before I close up my part of the presentation, is this map. This is a map of the 2020 census redistricting tracts around Baltimore. And this is basically based on race. And so this is a map that I made based on dot frequency. So each one of the dots represents two people. If we click on any one of the places here, you'll see the census tract comes up. And then what happens is I get this list of the total population, and then the breakdown of the ethnic breakdown of this particular district. So this is census tract 402-404. This is in Baltimore County, Maryland, has a total population of 5,239. Now, one of the things that isn't invariant is the racial characteristics. In other words, the racial makeup. And so if I take this particular district here, this is in Howard County, just south of Baltimore and to the west. 6,000 people live there. That's an invariant. So the total count of people who actually live there is 6,036. But because of the noise injected, the racial and ethnic data, which is not invariant, if I add up the races of all of the people who are in this district, it does not equal the total of the population. And this is the kind of thing that is really important when one is really looking at this data. One now has to take into account in doing any of these small area geographic analyses, whether that be from an epidemiological standpoint or a transportation standpoint, when one is looking at anything that has to do with income, that has to do with race or ethnic makeup, one has to worry about and consider the noise that has been injected into the data. So one is always going to be dealing with this sort of range of possibilities now, as opposed to actual numbers. So this gives us a range of solutions to some of the allocation problems, as opposed to a single solution. And so this is something very important. It is critical to the census and its viability, and it is going to be even more critical in future census work. At this point, the census appears, at least it does, think that it has solved the problem, at least from a differential privacy perspective. In other words, it has applied these constraints in order to give complete privacy, or at least as much privacy as possible to the individuals who respond to the census. But as computational methods become better and better, this becomes a more and more difficult thing to actually do. The algorithms that the census is using to do this are extremely complex. I cannot tell you how the amazing work that the people at the census have done to develop these algorithms. And they've released the algorithms to people for analysis. And so there's, like I said, besides my group, there's other people who are working on analyzing the actual structure of it and what it's actually doing to the data. So I did say before, there's going to be at the American Association of Geographers, there's going to be several big sessions on this subject, as it is, like I said, critically important to the cartography and how all of this stuff is playing out in the larger geographic analysis realm. And so really that's my part. That's what I really wanted to talk about. I invite all of you to come to the GIS Day on Wednesday. It's not going to be live. It will stream starting on at 1 o'clock on the library's websites. And there are four very good speakers who are going to be talking about this, and also talking about the redistricting problem and actually the difficulties in mapping redistricting using GIS and some other more advanced methods. So there you go. I want to thank everyone for attending and listening, and I can turn it over to our hosts and then to Megan.
Hey, thank you, John. I don't think I ever quite realized the mathematical implications of the current census. I've been working on the 1860 census here in Montgomery County, and it seems to be much simpler. But
yeah, I would imagine it's become a real you know, just the modeling that's being done by the census. One of the things that Deirdre Bishop has been really instrumental in doing is injecting these agent-based modeling methods in order to predict census turnout, allowing basically to each of the census districts to have things like an index, which is the volunteer response rate, and then using machine learning to predict what particular areas are not going to respond well based on the demographics from the previous census and from what the American Community Survey says, and thereby allowing them to go out and really target what particular places they need to have people on the ground visit. So there's a lot of very advanced mathematics going on. Just the creation of the address database itself, you probably don't know this, but an address database, how many actual addresses are in cities and towns all across the United States, is an incredibly complex problem. And now this is done by using very, very complex matching algorithms, which are basically taking very high resolution remote sensing imagery and matching them to satellite or to address data, updating the satellite data based on buildings that have moved. The agent-based or the machine learning models that they develop basically can tell, okay, this is a new house. I have to assign a new address. Let me check the new address database from the Postal Service, thereby updating the address database of the census. It's an incredibly complex computational thing. It's not just taking those things and putting them in tables. And it's also, as I said, become a very complex problem as far as reconstruction goes. Is the more accurate we get, there's a theorem called the fundamental theorem of statistical information, which says you cannot have an accurate statistical database without releasing some bits of private information that you actually want to keep secret. And the question is to know what those bits are and to know how to defend those bits against the people who want those bits. So yeah, it's incredibly complicated.
Okay, I guess just another observation from an historical archival perspective. What is the limit on privacy for these records? I thought, was it originally 70 years? Is that still?
Yeah, that's still, yes. Yeah, for the individual microdata, yeah. That's going to be updated, however. I think there's pending legislation to move that to 101.
Okay, thank you, John. I think, why don't we take a break for a few minutes and resume at 2:45.